Hello everyone. Today I'm going to work on my lathe. I want to make it cut more parallel again, because when things really need to be precise, I oftentimes noticed diameter variations or taper in my parts. This is not a video about leveling your lathe bed. Plenty of other people have already shown how to do that. The primary goal of this project is to measure and straighten the front V-way as best as possible, and I will also end up doing a spindle alignment. And at the end I will be showing some test cuts to indicate the final precision I landed on with this lathe. What I'm about to do to the front slideway cannot be done to every lathe, so be warned. But I will be demonstrating what I think is the cheapest and easiest way to align your spindle to the lathe bed. No reference bar or large micrometer needed, just an indicator and some material. So at least there is some information that is applicable to most lathe owners. I have labeled some timestamps, so if you're interested in specific parts of this project, feel free to skip around. The machine is in good condition, but it has some wear in it, which is to be expected after 63 years. I have noticed that turned parts have some shape to them when I really start splitting hairs when measuring. When turning short lengths, it's not really a problem, but on longer lengths, the diameter can vary multiple hundredths of a millimeter. There may be multiple causes for this, but in this video I will be measuring and addressing two contributing factors. Also, I must apologize. I put the cart before the horse, and in my zeal I have forgotten to make a test bar beforehand to compare part parallelism before and after the adjustments. But I think the end result will speak for itself. To start fixing the front V-way, first I need to be able to measure how much it has worn. This block will become a measuring tool which compares the positions of the flanks to the top crest of the V-way and will tell me how much they deviate. While I'm at it, I'm also making two more blocks with different geometry that I may need in the future. First step is to prep the stock. Say hello to my new coolant. Hopefully it will stay clean for a long time. I'm using the arbor I made in the previous video with this cartoonishly large saw. Frankly, this thing kind of scares me. I have some coolant from the lathe in a bottle here because the coolant system on the mill is currently non-functional. And it looks like the part has grabbed the blade. Despite this being a nicely machining steel, it appears the gap has closed and clamped the blade very firmly. I still need this part, so I persuaded the gap to open up and got the saw out. If you look closely, you can see the damaged edges on the cut where I hammered a screwdriver in there to get it to expand. That material will be milled away, so no harm done. Bulk material removal with a carbide 12mm end mill in a side lock holder. This end mill is getting pretty dull, but it still gets through this part. This is a new part and I have changed the end mill to a much sharper one. I can take much deeper cuts with this one without cranking so hard. This is what I was trying to do with the slitting saw. Provide a nice flat bottom for the 90-degree angle. But in hindsight, a small end mill does a much better job. Drilling holes to mount 5 bearing balls. This kinematic arrangement will sit in a stable position on the V-way. 3 balls for the first flank and 2 for the second flank. When all 5 balls touch, the block will be in an exact defined position without any rock or play, ensuring the measurement is stable and accurate. Even with potentially uneven wear in the flank surface, the 5 balls will always find a way to all make contact at the same time. The balls are pressed in with the quill straight on the mill. I have used a 7.9mm drill with 8mm balls. The drill will make the hole slightly oversized and provide a tight fit over the ball that is still easy to press in. Well, it looks like I forgot to slow the feed down when the drill was about to exit the material. This drill exits in the middle of the V on the bottom, and it looks like it instantly grabbed and broke clean off. It was surprisingly easy to tap the broken drill out of the hole with a punch from the other side and continue drilling. This hole, by the way, is for an indicator. The tip will probe the top of the V-way and compare it to the position of the flanks. The second block has a pin installed across the top. It will not be used in this video, but it can be used to map the actual straightness of the way. If one were to scrape or lap the lathe bed, you would need a block like this to measure the bed geometry with a precision level. Not this time though. We are not removing any material from the bed today. To start measuring the bed, the carriage needs to be removed to allow full access. I'm starting with my solid tool post, which is just held on with 3 bolts clamping the dovetail to the top surface of the cross slide. Next, the lead screw and power feed shaft have to come out. The power feed shaft is affixed with a roll pin, while the lead screw is keyed and will just slide off to the right. Removing the bearing block that supports the end of the shafts. There is a threaded taper pin which I need to remove. First, I clean out the threads with a tap. Since the head of the pin is subsurface, I can just use a stack of washers and a screw to pull it out. In this condition, I can just close the half nut on the carriage and pull the shafts to the right with the hand wheel. Now the apron needs to come off. It's pretty heavy, but I have a trick to not drop it on my feet. When loosening the bolts, I take out two entirely and replace them with longer bolts. This way I can let the apron down onto the planks in a more controlled way by unscrewing the longer bolts. You can see the long shaft on the hand wheel with the worm gear. That's where the rapid reverse power feed used to live. While I had this out, I took measurements and I will be making a shorter shaft to locate the hand wheel closer to the apron. The coolant line is held on with just one bolt. Fun fact, the carriage lock screw is one of the first parts I ever made on this lathe. It's made from an M10 socket head screw turned down to M8. Below the front and back ways, there are some keeper plates that keep the carriage from being lifted up. For example, when you're using a boring bar which reaches outside of the footprint of the carriage, it's technically possible to lever up the right side of the apron. These plates make sure nothing dramatic like that happens. The carriage of a lathe like this is quite heavy and needs to be moved carefully. I recommend using a crane, but I don't have one. And I'm not a lifter, but I am a climber, so at least I'll be able to hold on to it good. The feed rack needs to come off as well. These bolts clamp the V-way rail in place. I'm installing some longer bolts into the rail so I can hammer it up out of the slot. To be clear, this is not the first time I've been this far. Everything was a lot dirtier and tighter last time due to old corrosion. The first step in measuring is to establish if the slot is straight. I want to measure this with my precision level. In order to do that, I first need to jack up the left side of the lathe to have the bubble within its measuring range. It's very sensitive and reacts to less than 1 degree of rotation of the bolts in the feet of the lathe. I'm sliding the level along the bed length in equal increments, and I record the reading in every position. One division of the bubble moving corresponds to the angle change of 3 microns of vertical movement over the length of the level, which is 150 millimeters. When I graph the measurement, we can see that except for the first point, every measurement is within 10 microns level change. Disclaimer: this graph gives only an indication of straightness. It is not an accurate representation of true height variation, since the level was not fixed on feet and the measurements were not spaced out at the pitch of the feet, which were not there. The pitch was not even the same as the length of the level. What this graph does tell me is that there are small geometrical errors which go up and down. It's not a big slope. There are no deep holes or high peaks I need to worry about. I conclude that for my purposes today, I can assume this mounting surface is straight. Quick sanity check with an indicator used as a repeatometer which measures consistency of curvature. The needle does not move a lot, which supports my findings with the level. Next is the rail itself. I want to confirm that the bottom of the rail is parallel to the top. This would indicate that the rail was made precisely and that the top was possibly ground while mounted on the lathe bed. I use a comparator gauge with a 1 micron indicator because I want to see in detail what is going on. The gauge pushes the left plunger into the work with a constant force, and the indicator measures how far the plunger moves. In this image, I have zeroed the gauge and I'm going down the full length in steps to evaluate parallelism. The rail ended up measuring within 10 microns over the full length, and since we know the mounting surface is flat, the top surface of the rail can be used as a reference line to evaluate wear of the flanks. This is because the carriage only touches the flanks of the V-way. The top, in theory, is not subjected to wear. After reinstalling the rail on the bed, it's time to use the block I made at the start. You can see the kinematic pattern, which makes sure there is no rock or play while measuring. The indicator stylus in the middle compares the position of the top surface to the position of the flanks. I will zero the block at the end of the bed where the rail still shows original grind marks, indicating that it has worn very little in this position. I'm using the same 1 micron indicator. I have marked the positions of the bolts which clamp the rail down to the bed, and those are the positions I am interested in measuring. I have graphed these measured points as well. The numbers below are the bolt positions, with number 1 being the headstock end and number 15 the tailstock end. The measurements are written in microns. We can see a clear wear bias towards the headstock. This is no surprise because normally a lathe is used close to the chuck the most. The most severe wear is 51 microns deep in position 3. The wear gradually returns to 0 towards the tailstock end, likely because the variations in workpiece lengths this lathe has cut over its life. The leftmost position is also unworn. The carriage rarely touches this position because if you slide it that far to the left, you will be cutting into the chuck with a normal tool setup. Just for fun, I have combined the graph of the flank wear with the parallelism of the rail, and it's clear as day that we are measuring the wear with high confidence. To make this more intuitive, I have overlaid the graph shape onto the lathe bed in approximately the correct position. The wear is indeed where we would normally expect to use the carriage most of the time. With a reasonable assumption that the top surface has been ground while mounted to the bed, I will be taking the measured values as actual vertical wear. To correct the wear, I am shimming the bottom of the rail to lift the flanks up to approximately their original height. I have sorted and cut shim stock into strips which straddle each bolt location to ensure a solid bolted connection and to prevent unexpected bending effects from clamping the bolts. I have placed shims on 9 of the 15 total bolt positions. I'm using a spring steel shim stock kit which includes, amongst larger sizes, shims in 10 micron steps from 0.01 to 0.1 millimeters. In my opinion, it is important in critical applications such as this to not use stacks with many shims. If they get misaligned while mounting, it's asking for trouble. In this case, I was able to get to my desired size with only one shim per position. I'm putting a minimal amount of heavy grease on one side of the shims to stick them down to the bed so they don't fly away while I try to mount the rail back on. And here is some secret sauce. I'm going to use Loctite 603 to fill the gaps left between the shims. This is to mitigate the loss of rigidity which I have created by putting the rail on shims. Since I have reduced the supported surface area of the rail by about 70% by shimming and thus reduced its resistance to compression, it is technically less rigid than before. The air gaps between the shims offer no support. So the idea is that by filling the gaps with a glue that will harden, the bridge will be supported by solid material. Yes, the Loctite is not as stiff as cast iron, but it's a lot better than air. I have specifically chosen 603 because it is relatively fluid and it's rated to cure in very small gaps down to a press fit. I have considered other glues like epoxies or acrylic glues, but from what I could find, those tend to not cure well in very small gaps. Any excess Loctite will squeeze out into the central channel and will not create any unwanted hydraulic effects. I have tested this joint configuration before I started and found that this Loctite is not very strong in tension, so I expect to be able to remove the rail again should that be necessary, especially when starting from the tailstock side to create a peeling action and concentrate the stress to break the bond. When reinstalling the rail, I'm making sure to not disturb the Loctite. I'm installing long bolts to hold the rail approximately in its correct position. The thin parallel on the left ensures the rail does not tilt and disturb the shims while I'm getting everything ready. I'm pre-installing all bolts into their places. Once the tailstock side has been partially started in the groove, I remove the parallel because there is no more danger of tilting anymore. I'm preparing all bolts to pull the rail down partially into the slot. I don't want to pull it all the way down just yet. The critical moment has arrived. I'm tightening the bolts from right to left with an impact driver to moderately clamp the rail down as quickly as possible over the whole length. Ideally, before the Loctite starts to set, I want to tighten all the bolts by hand. If there would be any gaps left, I'm hoping the soft blow hammer can close them down. It's probably completely unnecessary considering the clamping force of M8 screws, which can easily pull 2 tons per piece. After putting everything back together, it's time to see what I'm working with. I took a small cut in steel with a relatively sharp tool, but it hasn't been lapped in a while. That is 12 microns deviation over a short distance. Needless to say, I was not impressed. Here you can see me in the process of losing my mind trying to align this supposedly high quality test bar while mentally compensating for runout. This turns out to be an exercise in futility because I'm pretty sure this bar has almost 10 microns of error in its shape and or parallelism. I'm using a MAR millimesh indicator which has plus minus 50 microns total measuring range. These are a high quality and sensitive indicator with 1 micron resolution. I have a newer and cleaner one also, but this one still works good. I forgot to turn on the camera, but as you can see I turned an aluminium test bar with a fresh polished sharp insert, and I'm measuring it at different points with a micrometer. I'm walking away to record the reading into a table and to make a plot. These are the readings in a graph. The values are incremental with the chuck side set to 0. The part is getting larger in diameter as it gets away from the chuck. The red line is a linear trend line and it illustrates that the taper that I'm turning is very consistent. Let's look at that taper with the millimesh. I apologize for the framing, but traversing the tool side of the part reads close to 0 over the whole length because that's where the tool was cutting. The millimesh is so sensitive that it picks up surface undulations and inconsistencies, but it's within 10 microns. However, when I indicate the back side of the part on center height, we are presented with the exact taper I measured with the micrometer. This taper can only mean one thing. Well, actually it can mean 2 or perhaps even more things. The first is the lathe bed can be twisted on its leveling feet. But from experience, I know that this lathe cannot be twisted by that much over this length, even with one of the 4 legs hanging in the air. The second reason is the headstock is not correctly aligned to the bed. I have not touched the headstock alignment before on this lathe, assuming that no one else in the past had adjusted it. Well, today's the day. There are 2 nuts in the quadrant housing and 2 bolts under the spindle nose. I'm actually lucky that this lathe has flat contact between the headstock and bed. Some lathes, mainly older lathes, have V and flat interface between the bed and headstock and can only be adjusted by scraping or grinding. I also found this lost little set screw at the back of the lathe, which turned out to actually be a pusher for the headstock alignment. The movement on the millimesh here is actually me turning the screw at the back to adjust the alignment. I'm shooting for 20 microns to conservatively split the difference of the taper I measured on the test cut. With the headstock adjusted, let's compare the millimesh reading on front and back side of the part. Looks like the front and back are both really close to 25 microns deviation. In theory, the spindle should now be very parallel with the bed. With the millimesh on the back of the part, remember, we are measuring taper directly. Speaking of which, it's mainly measuring surface noise at this point, but if we ignore the weird non-repeating peaks, it looks like the adjustment was successful. The parallelism expected from a lathe part is not only dependent on the lathe itself, but also on the parameters of the cut and the sharpness of the tool. In this case, we have a negative geometry insert tool. It generates enough cutting pressure to throw off parallelism by 22 microns, even on a light cut. The deflection, in my opinion, happened mainly in the part, not in the lathe. To demonstrate, here I'm taking a much heavier cut in a material that has a larger diameter. The larger diameter makes this part much more resistant to deflection, meaning it's more rigid. As a result, we can see a completely different taper in this part. It's not even a taper. It's some kind of spool shape, which I cannot really explain, but it's also only 5 microns deep. So if we optimize the finish cut for the lowest conceivable tool pressure, this is where we arrive. Brass, an easy cutting material, cut with a super sharp polished carbide tool at a very small depth of cut and a slow feed. It's cutting 10 microns from the diameter. And there it is, people, a test piece cut parallel to the limits of my measuring equipment. The effort seems to have paid off. The lathe was definitely not able to do this before the bedwork and headstock adjustment. The length of the cut is about 70 millimeters and the stock diameter was 20 millimeters. The parallelism deviation is 1 micron. And now the real test. I don't make parts from brass very often. Some of you will recognize this bar stock. This is 42 Chromo 4 high strength steel. Let's see what the lathe will do with this. I'm using the same polished sharp carbide tool, and by eye it looks like I'm taking off a little bit more than the brass. The finish looks dull, but it feels smooth. 2 microns parallel in 42 chromo 4 over 70 millimeters distance. For a 63-year-old lathe that had 50 microns of wear in the bed, I think this is very respectable. Now that we have seen the measurements, adjustments and end result, I am sure you have some questions. I will be answering some I can think of now. Why did you not measure and adjust the back flat slideway? The back slideway rail is bolted horizontally to the back side of the bed and cannot be shimmed like the front rail. In addition to that, I expect less wear on the back rail than the front, because for most operations, the cutting tool is closer to the front rail than the back rail. The rear slideway is also too narrow for me to measure conveniently with my level. In a hypothetical future project of further accurizing the bed, I would aim to address both front and back rails, which would involve using better measurement techniques. I would need to evaluate actual slideway straightness and twist and start removing material by grinding or lapping. This would overstep this project's goal, which was to correct the largest wear area in the lathe bed. Why did you not test the parallelism further down the bed? For long parts, extra support is needed, like a tailstock or steady rest or follow rest. In those cases, I would just be testing the precision of alignment of the support, not the lathe bed directly. Since the lathe bed was measured and adjusted using a consistent method over its whole length, I am confident similar results can be achieved down the bed as compared to what we found close to the headstock once the necessary supports are suitably aligned. Lastly, not a question, but a point on skim cuts versus balanced heavier cuts. I realize taking short, light cuts is not time efficient and requires sharp, fragile tools. Normally, I would be taking balanced cuts, which are heavier to arrive at my target diameter with predictable precision, good surface finish and hopefully small curly chips using negative geometry carbide insert tools. But whether the diameter comes out parallel is dependent on the design of the part, whether it is long and skinny or short and stout. In cases where the part deflects too much under the cutting forces, it is sometimes necessary to make or buy a tool that is very sharp and allows the lathe to cut uninfluenced by deflection and transfers its precision into the part.